Hopefully, you're here to hear me talk about event-driven.net. So the goal of the session today is to really introduce people to some of the core ideas that matter when we do eventing and show you some examples. It's not really kind of training, and there's quite a lot of depth that we won't be able to go into. So this is a dullish slide which says that I'm old. But the key point is I work currently for Just Eat Takeaway, and I have nothing to sell you, right? I'm not a consultant or a vendor. There's nothing. I'm just trying to share my experience with you. The only thing I do have to sell you is that I'm the originator of a .NET messaging framework, which is open source, called Brighter. We've been around for 12, 13 years. We compete with Mass Transit, Wolverine, Rebus, all the others, etc. I'll talk more about those again in a minute. It's not just me. There are loads of contributors. You can go and see basically that on GitHub if you like. What we're going to talk about. So the first thing I want to talk about is just what we mean by being event-driven, right? What does that actually, where do we use eventing typically, and how do we use it? Then I want to look at the sending side of messaging, the producers, and show you how producers work and some of the things you need to consider and show you some code. Then we're going to look at the consuming side, how we then consume those messages and show you some code. We'll then run some demos. Anyone at my demos yesterday? I've sacrificed to the demo gods, and I've got a video version just in case. Talk a little bit about pipes and filters, not in depth, just to really give you an idea of how messaging applications can string together, and you get things like stream processing, and then we'll have an overview of frameworks and middleware. So it's kind of an overview. We're not going to show you quite how deep the rabbit hole goes. I teach messaging workshops at various conferences. It takes me about 2 days, and I'm still not really done. But it's enough to get you started and give you signposts to the right places. All right, so let's talk about what it means to be event-driven. So on the left-hand side, we have the typical synchronous application that you write a lot of today. So that might be OpenAPI, GraphQL, gRPC, Thrift, SOAP, doesn't really matter. The point is that both parties to the conversation need to be available at the same time for it to succeed. The analogy I often use is a phone call, right? If I phone you up and you're not there, my communication fails. On the right-hand side, we have what we think of as an asynchronous conversation. So in an asynchronous conversation, which is typically messaging frameworks like SQS, Kafka, AMQP, MQTT, but also file transfer by things like S3, really messaging is just very sophisticated file transfer. Then both parties don't need to be present at the same time. That's because we rely on something called store and forward. I write my message as a producer to an outgoing channel where it's kind of saved. At some point in the future, the consuming application can come along and consume it. Now, obviously, ideally, you may have lots of situations where you want low latency and you want that to happen very quickly, but the point is that both need to be up at the same time. That means the service in the right-hand side of the diagram, the async side, the service on the left is not dependent on the uptime of the service of the right. It just sends its message and gets on with whatever work it is. If it expects a reply, that reply comes back on another channel at some point in the future, and it has to write a handler to say, hey, I'm going to receive that reply when it comes, and I'm going to action something. So one of the things that's different about the left and the right is typically on the right, you are storing state, so that essentially you say, I make a call, I store some state, and then later on, I may want to get that state back out in order to process the reply. You can use a natural ID like the order ID. You can use what we call a correlation ID, just a randomized number to link those two things together. And that's really the difference between asynchronous and asynchronous. Most of you probably, if you're doing something like organizing dinner with your friends nowadays, will tend to use messaging. And you do that because it's very unreliable to try and phone everybody. And it's exactly the same with software. So you do asynchronous all the time. The other thing I quite often talk about is asynchronous is how the world worked before computers. Most businesses, you sat at your desk, you had an inbox and an outbox. Work arrived in your inbox, you did it, you put it in your outbox. Most businesses worked exactly like messaging systems do. All right, so one typical application that we tend to see of messaging is what we call a task queue. Very common in the Python world because of a tool called Celery. So the idea here is that when I receive some kind of web request, rather than handling it immediately, I want to simply put the request onto a channel, typically a queue, right? And then I'm done. I can then go and answer another web request and keep working and receiving more web requests. The receiver then pulls that request off the channel, off the queue usually, and then actions it. Typically, it might be talking to something like a database. One of the advantages of this model is that the receiver can make sure that it's not overwhelming the database. It can effectively throttle the rate at which we call. So we don't get that kind of run out of basic database connections error, right? Because effectively the receiver can say, how fast can I go? Now, you will get a problem if the sender's putting on much faster than receivers consume. We can do that about a bit later, but you can help yourself deal with surges in traffic. So HTTP has an asynchronous option. I don't know whether who knows about 202? Okay, a few of you, yeah. So what you do is basically return 202 accepted. You're saying essentially, I have your work, I won't lose it, but you should go on about your business, and I will reply to you later. And what you typically then do is queue the work item for the request, and then go and action it on the receiver. But how does the client know, that we're done? So a typical model is to use the location header in HTTP, and in the location header, you put a URI for them to check. It's either, if I'm creating a resource, like I'm saying, okay, can you create your application form here? Then typically one way of doing that is to give you the URL the resource will have when it's created, and they just keep polling that resource until they stop getting a 404 when you finished your work. We can get a bit more complicated than that, though, because we might say, well, using 404 for not found temporarily might be confusing to my users, and I might want to also, if it's a particularly long-running operation, give you some idea of progress. So typically what we do there is on the receiver, we will update some kind of key value store, and in that key value store, we will have something that is effectively tracking the progress of the piece of work so that we can update it when it's done. And then what the web request can do is provide a link that says, hey, when we're done, this page, while we're in progress, this page would show you the progress, and when we're done, it will redirect to the created resource. Okay. And that's a very typical pattern using messaging for offloading work, and it's a very good way of scaling, right? The bigger use case, I tend to call it reactive nowadays, but event-driven architecture is really the same word. It's when we're using it for communication between our applications, microservices, if you will, in order to essentially say we want a more reliable form of communication than a synchronous one. And we also typically want independent deployability. I can deploy my service. I don't have to worry about actually testing with other services that I call, because I just send a message and receive a message, and I can fake that out. So here you can see we've got 4 applications and communication between them, slightly different form. So here what we're seeing is that the first application says, you have an operation I need you to perform, and I'm going to invoke that, and then I will get on with my business, and you can tell me when you're done. So maybe I'm saying to you, can you take a payment for this basket at customer checkout? Let me know the results of that. And that's on channels are unidirectional, right? So I send you that message, and you then reply later using another channel, the reply channel, which we typically pre-agree, although sometimes you send it in the header of the message where to look for the reply channel. And that reply channel says, here was the outcome. Typically, we think of the outgoing as a command and the response as an event. We can get complicated and think of a very full, fat response as a document, right? But we're saying, okay, here is my message, and then another channel, here is my reply, and by correlation ID, I tie up and go, okay, you were the answer to this question, customer paid, customer's payment was rejected. The other model we see on the other side is, rather than using a queue, we may use a stream, and what we're going to say here is, I want to broadcast information to a number of people about something that happened. Here, presumably, I'm updating a whole lot of people to let them know that that basket has been paid for. Right. And that is essentially what typically people think about as pub sub, this idea that I'm broadcasting to a number of given consumers. And those are the major places that we tend to find people using messaging. And the argument in reactive architectures is that all communication between services should be basically asynchronous, because that allows you to scale, recover from failure, and makes you more responsive. Okay. So, how do producers work? 3 little diagrams here. So typically, we are sending a message onto a channel. The channel is just really an abstract term we're going to use because we don't want to talk about queues and streams all the time. I'll explain the difference between queues and streams a bit later because it's too complicated to explain at the beginning. But don't worry about that for now. So we send a message to the channel. So here, a queue is typically kind of a one-to-one. I am giving you a request because I'm invoking an operation. I know who it's going to. It's going to the payment processor, and I want you to basically take a payment for it. And here, as we said before, we can send a message to a stream. Many applications will listen, such as, hey, payment was taken. There's also really the concept of a broker. Now, you'll see in some messaging middleware, Amazon particularly, the broker is separate from queues. So Amazon has a queuing system called SQS, and I can use that point-to-point between two applications. But it also has a broker system called SNS, where I can send a message and anyone subscribed to that topic will get the message. And then effectively what I do to subscribe to that topic is I use a queue. All right, so it just intercepts this thing sometimes called a recipient list, which effectively says who should receive a copy of the message when you have a broker. So the difference is one-to-one or kind of one-to-many. Right? If you're using a broker, it becomes one-to-many. Azure Service Bus also has this idea of subscription, right? Where effectively you can say, hey, I'm going to subscribe using a queue, or I'm going to send a queue directly, right? And it's commonish as an idea, this separation between the two. That causes some confusion because, in a sense, both brokers using queues and things using streams are both doing pub subs, and the streams typically talk about sending a message to a broker, even though really it's a stream. So the whole terminology here is kind of messed up, right? But we'll explain a bit more detail about streams versus queues later, so to help you. Okay. The other thing that we're going to get into quite early on, although typically I often leave it later, but I want to do it early on, is about what we call transactional messaging. So there's a danger when I send a message that failing the message sends. And if I am updating a local entity, right, so say I'm updating the order to show basically that it's payment pending, I would really like that message to have gone, because otherwise my status is not correct and someone else looking, if I crash or whatever, going, well, you know, I don't know quite what happened. I've lost the payment. But there's no transaction that spans both our messaging framework and our database. It used to be the case with something like MSMQ that you could do that along with SQL Server, but those days are a bit in the rearview mirror, and typically we're working with different vendors with different requirements, and it's very hard to do a transaction that encompasses both your queue or stream and your data store. So that creates a problem, the potential risk of inconsistency. You could try thinking, okay, well, I'll reverse the operation, and I'll always send, and I'll only basically do the DB write if the message sends. but then you could have sent the message and not done the DB right, in which case effectively you told downstream a payment pending, but you haven't saved it upstream. So what you typically do is say, the first thing I'll do is write both the change to the entity that I want and the message to what we call an outbox. It's just a table inside your database. When you hear people talk about outbox and you go, that sounds really crazy, it's just a table inside your database. So you can encompass both in a transaction, and when you encompass both in a transaction, then essentially you now know, hey, I've got a message pending in my outbox if I wrote to the entity. And as a result of that, you then read the outbox in order to effectively then send the messages from the outbox, rather than calling the messaging provider directly. Now, what you can do for optimization is you say, okay, I'll give it one try to send it now, but if I fail, I won't worry about it, because a separate process, we typically call it a sweeper, will be running and effectively reading my outbox, looking for unsent messages and sending them. There is an issue here, and that is to do with the fact that you can get yourself into a situation where you don't know whether the fact that your message is not marked as sent in the outbox means that it wasn't sent, or you just didn't update the outbox correctly to show that it wasn't sent. So downstream, you have to cope with the fact that messaging says at least once guaranteed delivery, and you may receive a message twice. Either that has to be idempotent, in other words, if I receive the same message twice, there'll be no side effects, or you typically have to use an inbox downstream where you say, hey, if I've seen that message before, reject it. Okay, yeah, all right. So those who came to my talk yesterday, I'm going to basically use this as an example in some code of the Calvin Hobbes transmogrifier, because I got bored with the hello world. There's a little CLI, you enter who you are, what transmogrification you want, you produce that message, and the transmogrifier picks it up, reads it, and transmogrifies you. It's just slightly more interesting than hello world, right? Okay, so let's talk about how we send a message in Azure Service Bus. So this code here, what we're saying is the first thing I want to do is add it to an outbox. Now I'm cheating because this is demo code that's up on my GitHub, Ian Cooper, if you want to go and look at all the code later. And I don't actually have a unit of work. So in other words, I don't have a transaction that is spanning both my outbox and an entity right, because I don't have an entity right? But just follow along with the logic. That's what you need to understand. I put it in the outbox and I say, okay, here is the message that I want to send. Then I effectively compose my service bus message. Then I attempt to send, add some additional properties, like creation time, UTC, and name, because sometimes it's not just the data I want to send, but metadata about the message. So correlation ID typically would go in here. And then I go and I send the actual message. And that puts it effectively onto my desired channel, be it a queue or a subscription. And then when I've sent it, if I get to the, if I don't crash out of that line, I can essentially say, okay, I can mark it as async. What I'm not showing here is otherwise you would catch the exception and you can mark it as abandoned, where effectively you say that message wasn't successfully, not abandoned, you can mark it as unsent. So, abandon something else. All right, so dispatcher at the top, I'm configuring the service bus. You can configure retries. So before you get something shoved into your outbox, it's helpful to have some kind of policy where you say, how many times am I going to retry? Because most errors are very transient, and typically a lot of errors go if you retry almost immediately and then with a slight back off from that period. And then you create effectively your service bus client. So that's what we're using in the code before. We're going to create a sweeper that runs our outbox. This is just, you don't have to worry too much about the detail on this one. It's a hosted service with a timer, and the timer is going to fire every so often. When the timer fires, what we're going to do is read our outbox and find any messages that are still pending, and we will essentially send those. So this is how we send the message again, right? We get it out of our outbox, we convert it into a message. We may add some additional properties. to show that essentially this ended up being sent by the outbox rather than original send, so that we can keep track on what's happening to our code. So you can see here we're saying get the service bus message, add additional properties, send message async, and mark the status as basically async. And you can see here actually we are catching the failure. We show you on this one where effectively we say, okay, if in the event that we didn't actually send, but it's a transient error from the service bus, we'll just ignore that because it'll just stick in the outbox and we'll send it next time. We get some other kind of exception. So it's effectively telling us it's a permanent error. We may choose to mark that as failed to deliver. So we don't keep trying to basically deliver things that are causing a real problem. Okay. So Azure Event Hubs, which is the other kind of Azure item. A lot of code there. Sorry about that. It gets a bit harder here. But you've seen a lot of this before, all right? So it's very similar. We're basically adding stuff to the outbox. And then what we do with an event hub is we're going to go and create a batch. Because that is the way kind of event hub tend to work. They tend to assume you are batching data to them because it's more efficient. Here we've only actually got one individual record that we want to send. That's okay. We're going to just create that event data, and then we'll add it to our batch. And then as before, we're pretty much going to add some additional properties that we want to pick up so that we have this metadata about the messages that are flowing. We're then going to do a send async, and then again we will mark the status basically as complete in the outbox if we successfully send, and if we don't, we will essentially say, okay, there's an error, and hope that basically the sweeper then picks up that message and sends it later. All right. Okay. Again, very similar. Both of the APIs are incredibly similar. We are effectively going to just configure our event hub in order to allow us to retry the operation in the event, essentially, that it fails. And again, similarly, we're just going to read effectively for a pending list or in the outbox of items that we have to send. Here, we'll actually genuinely use a batch so that we can batch up all the items that are currently pending in our outbox and dispatch them all at the same time, and then we'll mark the status as complete if we don't get an exception. Typically, you may decide that if you're doing something like writing to event hubs, you can just rely on an outbox sweeper to do the work for you, because it will batch things up nicely for you typically, and you can kind of say, I don't have to do an immediate send, I just let it do a batch process in the background. We're showing the sweeper as a hosted service. That typically isn't what you want to actually do outside of demoware, and that's because you only want to have one sweeper running, and so you need something that's going to say, okay, how do I make sure that only one sweeper is running? Typically, we tend to run it in a separate process, and then in that separate process, we'll use something like a distributed lock on a row in a database in order to make sure that only one of our potential sweepers is running at any one time. But if a sweeper crashes, something else takes over. So typically, your sweeper is a separate process. You're running more than one instance, and you're using a distributed lock. Here, for simplicity, we're just basically making it a timer. The other thing you need to know is that when we are producing messages, they have different types of semantics as far as we're concerned, right? Even though people talk about messaging or eventing, those terms actually have some fairly specific meanings. So messaging is when I'm sending something with intent. Typically, I'm trying to invoke some operation that you provide. Eventing is when I say, here is a fact, and I want you to understand the fact that I'm giving you. Messaging typically requests an answer, or transfers control, or transfers value. So in other words, it says, can you tell me about X? Can you do this operation and I will wait for the response? Or effectively, I no longer own this, you can now have that. Typically, messaging is, eventing rather, is things you report on. So someone has performed some action, other people may want to know, and I don't have any expectations about how or if you will process it. Whereas with a command, I'm either doing fire and forget, don't expect a response, or I'm doing some kind of request reaction where I expect to reply back with the value that I've asked for. With eventing, I don't really know what you'll do with it, if anything. And that's okay. I'd never get a response from eventing. Messaging is part of a workflow usually. In other words, I'm conducting some work myself in my calling app, and I pause for a bit in order to get a response from you, from asking you a question or invoking or asking or giving you a command. Eventing is typically concerned with history, and applications that are reading the events are typically concerned with context. Now, you may see older terminology which refers to the left-hand side as commands and the right-hand side as events or documents, but the messaging versus eventing is a more modern context for that. It is all, to some extent, semantics that we are overloading over certain characteristics, which you'll see in a second. It's concerned with the future, concerned with the past. So those are the old names. If you're interested, you may see that, for example, the book on event-driven architectures is Gregor Hope's Enterprise Integration Patterns, a terribly named book for what it is. It's great, but typically that's the older model. Messaging is basically a command, and eventing is event or command document. Part of the reason for change is because it might not be a command, it might be a query, for example, might expect a response, right? So that's a change of names. So when we think about queues and streams, and again, we'll explain them in more detail a bit later, but queues is like Azure Service Bus and Azure Event Hubs or Kafka, if you came to my talk yesterday, as a stream, and typically messaging uses a queue. Messaging uses a queue because it's essentially a discrete piece of work, and I want someone to pick up that discrete piece of work and do it. I'm typically invoking an operation, so typically I say, someone should service this, hopefully only once. Streams are less good at this because essentially the thing about streams is that they lack certain abilities to do things like retry, etc. And we'll talk about those in a little bit. Whereas events, essentially queues are not so good at because I consume the queue as I read it, so it's not replayable by others. So everyone has to have a copy, which means essentially that I'm using more compute and resources. And again, we'll cover that again when we talk about consumption. Okay. Messaging tends to include, though we tend to often refer to an event being the response to a command, take payment taken, you'd think of both of those, if it's a conversation, as both being messaging. Okay. Talk about consumers. Okay. So consumers basically rely on a thing called the message pump, or sometimes people call it an event loop. And so what I need to do in the message pump, which is the heart of any consumer application, is I need to read the stream or the queue and get messages off it. So the first step is always get message. Having got a message, what I've actually got is something which is in whatever protocol that messaging framework describes, and the data in it could be text, could be JSON, could be binary, I don't really know. So the next step is to translate the message. In other words, take whatever protocol format it has and turn it into a C# class or record, right? I need to turn it into something I can now deal with programmatically. And typically, our response to owning one of those messages is to do what we call dispatch it, so to give it to a handler that will then run some code. Why do we do it this generic way? Because it enables you to write generic message pumps, which can be used for a whole range of consumption inside your application, right? So you can, if you're writing an application, you write message pump, I can use it in 3 or 4 different places. There is, out of the box, there are message pumps for Azure Service Bus and Azure Event Hubs. We'll show you the one for Event Hubs later, but they also have this model in the sense that they pass you the message that's been retrieved, and you're going to have to translate or dispatch it. And then basically you handle the message. So it's just your application code. So when you get a message pump running, it doesn't look that distinct from something like Minimal API, right? Minimal API is just calling your code. it has essentially absorbed all of the cost for you of determining that you've got an HTTP request, parsing it, etc., and just hands you something to deal with, and then you respond. So you want something very similar for messaging. You really want to just basically say, here is basically a C# class or record that represents the value you've been sent. Please handle the fact that you've received a message. We may fail to get a particular message off the queue, in which case we would put it on what's called a dead letter queue or dead letter channel to say, hey, this is kind of undeliverable, and therefore we should have a human being inspect it later. We might fail to translate a message. Typically, misconfiguration, someone sent me a message that actually belongs to somebody else, or there's been a change basically in the schema that someone hasn't told me about. And so quite often they get put on an invalid message channel or queue to say this is actually probably a good message, but I can't interpret it. Often people are slightly stingy with their resources, so they'll use essentially the dead letter queue to also be the invalid message channel, and that's okay, all right? Provided you have somebody whose job it is to go and look at that queue and interpret what they've seen, and that someone will get an alert or a ticket that's building up, and they need to go and inspect it and action whatever the problem is. Doesn't really matter if those are both the same channel. And a failure to dispatch, in other words, essentially I received a good message, I've translated it, but I can't find a handler for it, is always configuration, right? You haven't basically configured your handler that responds to that type of message. If we have an error in the handler, we get a choice. If the error is not transient, in other words, no matter how many times I try this, it's not going to succeed, generally because of the state of the body of the message I've received, I can't succeed with that, whatever the failure is. I would typically just use my normal process of logging that error and having people pick that up. Some folks like an error queue, but you're just building up more and more work, and typically the problem is at this point no longer the message. So no one looking at the queue will diagnose the problem. Typically, the problem now lives probably recorded in my logs, and I need to go and find that log in order to interpret what happened. If you are using a queue, and we'll come back to the problem with streams later, and you have essentially a transient error, for example, the database doesn't appear to be up right now, so I can't save anything to it, you can effectively re-queue. So you say, put this back on the queue. In quite a few cases, messaging middleware, you can say re-queue with a bit of a delay. Right. And then say, try and process that again later. And that's effectively a cheap retry. I'll show you how that works in just a second. Frameworks differ. Rather, messaging middleware differs. So RabbitMQ does re-queue with delay well, others don't really. You may find that if you're like a messaging framework like Brighter, so our V10 is just out, and our V10 will include support for scheduling stuff using a typical .NET scheduler like Hangfire or Quartz.NET, and we'll lean on those and then just schedule that to be retried at a delay for you. Okay. Typically, you may need to, if you're going to want to write a generic message pump that you're going to use in your application, you typically want some registry which says, where do I go to figure out how to serialize and deserialize this message? In this case, it's basically deserializing the wire content, right? How do I, on this queue, what does the message look like? Oh, I need to basically convert that this way, right? And typically then, if you also need to dispatch, you want a registry of handlers. I want to look up this particular handler for this particular type, and I'll pass it the actual message. Okay. Queues work by effectively saying, well, you've got a copy of the message on your queue, and I can put stuff on the letter channel if I need to. Streams, really, you can conceive of them, if you can, my Kafka talk yesterday, as just being a append-only file. and you are all sharing reading of that file. So Azure Event Hubs you can kind of conceive of as a really very reliable file where you are appending records to, and Azure Service Bus is a queue where you are adding items to it. And that's important for the following reason. So typically what happens with the queue is as follows. The first, if I've got multiple consumers, the first one comes along and it says, okay, I'm going to read the first item on the queue, and I'm going to lock it. And I'm going to lock it so it's not available to anybody else to process. Somebody else who wants to process has to read past me and grab the next item in the queue. That way, we can scale out the number of people reading the queue, but we don't preserve order. When I've basically finished, typically I will do an ACK which says, or I do an ACK or an ACK to unlock it, right? Whoops, a daisy, I'm going the wrong way. If we succeed, that's a little red, supposed to be an eraser, a little red eraser. If we succeed, what we say is delete it off the queue. That work is done. Nobody else should be doing that work. I have done that work, right? So that's deleted, and nobody else can get hold of it. If I don't succeed, for whatever reason, doing it, the way you get retry is typically called a knack. And what you're really doing in most cases is just saying, unlock it. Unlock it, and somebody else can pick it up. If I crash while I'm attempting to process it, typically the middleware will notice that the heartbeat's gone from me and unlock any messages that I had locked, making them available for other consumers. And that gives you some resiliency. Because if the receivers crash, you don't really care, right? The work is still on the queue, the work is safe, you can come back and process it. That gives us competing consumers, which is what you'll see as the word used for how you scale out the number of receivers of a single queue by essentially allowing everyone to read past each other. Okay. All right, consuming a message in C#. So this is basically Azure Service Bus. So you'll see here that we are going to basically run a message pump, and in that message pump, if you look on line 1, while this cancellation token is cancellation requested, I'm creating a loop that goes on forever, sort of while true, until somebody hits a cancellation token. In the demo app, that's basically someone terminating the application. And as I spin round, what I do is at the top in line 4, I'm going to read a message off the queue. And if I've got a message, then I will essentially try and process. If I haven't, there's nothing, the queue is empty, I'll just spin. Typically, you might actually want to put a delay in here to yield control a little bit. And then with that message, which is essentially an Azure Service Bus message, I am effectively going to translate it. In other words, I've got a Lambda function that I'm passing into my message pump. And what that does is say, take this message and turn it into a thing I can recognize. And then I'm going to handle it. So I will pass that data type to my handler that I've also passed in as a Lambda expression to get the work done. I'm not doing complicated registration because it's a demo and we get lost. If that result succeeds, in other words, I've successfully handled it, then I will ACK that completed message. So that basically is delete and take it off the queue. And if I fail, then I abandon message and somebody else can pick it up later. Unless it was essentially a unreprocessable error, in which case I should have an application error instead. This is what it looks like to call it. So I'm calling my message pump. I'm passing it a translation function. So in this case, it's basically creating a transmogrification from the subject and body of the message. I'm just using strings rather than JSON for simplicity. And then most of that is spectre.console code and a handler, which is really saying just spit stuff out to the console. Fans from yesterday may remember this demo. Streams. What happens with a stream is, I read the next, slightly off, but you read the next message in the queue, and the second message reads the same message in the queue. Sorry about that, should be the point to the same message. Because what happens is that each consumer reads the entire stream and marks its offset. In other words, how far it's got into that stream. Each one in turn is reading the whole stream. So there is no competing consumer model. Okay. So what streams do is have partitions. So a partition says, for a given, usually key, a hash key, I want to send everything to the same partition so that it will be in order for that thing. So for example, I send everything for the same restaurant to the same partition, such that all the work for that restaurant will be in order, be on the same, because it's placed on the same partition, but another restaurant may go to the other partition. So streams use partitions to scale, and typically when you set up your Azure Event Hub, it'll ask you how many partitions you want, and you're really working on, well, how many consumers do I need, and how many, in order to keep pace with the rate of arrival of the work. So it takes me 30 seconds to process a piece of work, but a new piece of work comes every 15 seconds. I need 2 partitions or 2 consumers. All right. So this is how Azure Event Hubs looks. So here, what I'm actually doing is I'm going to use the built-in message pump called Event Processor. And that effectively has a couple of callbacks that you register with, a couple of events. And your method that subscribes to those events, one's for, hey, I successfully got a message off the stream, and the other one is I didn't get successfully, I got an error. One of the reasons for using Event Processor here is dealing with partition management is complicated. Actually, if you came to my talk on Kafka yesterday, Kafka does a lot of work for you in the client. The equivalent of doing that in Event Hubs is to use the Event Processor, which is doing most of the work for you. There is documentation on how to write this by hand, but it is more complicated. So what we're going to say is if we successfully get past a message, then we will do our translate, and then we will do our handle just as before, and obviously then we have some stuff to say, I got an error, nothing seemed to work. Okay. And this is how we call it. We say, start processing async, and then we have to effectively, if you like, spin, and in this case, we're just using the tactic of saying, set an infinite delay until we're cancelled. And then at the end, we will stop processing, because we have to send an instruction to tell the processor to stop, because it's running away on a separate thread. Okay. Right, someone offer a prayer to the demo gods, and we'll see whether we can actually get this to work today. All right, let's start with Azure Service Bus. Let me clear the spoilers. Those who saw Kafka yesterday, it's pretty similar. Let's just see if we've also got this. We do. Okay. Quick look at the program file. I'm not going to go into it in detail because of time. Essentially, what's happening here is we're taking in some values and calling the dispatcher. It does transmogrify. This is the code you've seen before. This is all up in GitHub, so you can go and inspect it at your leisure. And that's essentially creating and sending the message. And over here, we have the consumer, and the consumer has its message pump. The key part of that is this big while loop that effectively listens for a message, translates, handles effectively, and then decides to ack it, say it's complete, or abandon it afterwards. So, if I do .NET run here, I can't spell today, it'll ask me my name, and I'm going to be Calvin, because it's from Calvin and Hobbes, and I'm going to turn myself into a tiger. And it says, I've sent a message, right? So it's basically changed the status of the Outbox and said this is now pending, and effectively, I've sent the message across the other side. We can go and look in this one. I need to refresh it. So this is that essentially subscription on Azure, and it takes a while to show up sometimes. We'll give up in a second. Okay, as always. Right, we won't keep trying to fish for it but what you can see is that typically you'll see a message there because the message just sits there waiting in a store and queue fashion for us to then go and consume it. So we're going to basically begin the transformation. It's going to go and find that transformation, right, and says to us, okay, I have read that message successfully off the Azure Service Bus. All right. Event hubs, it's pretty much the same. I'm going to show you the code in a second. Let's clear that. So you've seen this code. Essentially, we've been talking about it. So the producer is just again in the dispatcher. You can check on Outbox and Outbox Sweeper and stuff when you look at the code. But you can see here, we're adding to the Outbox in step 1. Step 2, we're effectively creating the message that we're going to send. Step 3, we actually send that batch. And step 4, because once we've sent the batch, we'll mark it as complete. And the sweeper in here would effectively pick it up if it failed at some point. And in the consumer, we do here, yep. Essentially, what we're doing in this side is we're defining the callbacks on those events, right? So we're saying a process event handler, translate and handle. And here we're saying start processing async, etc., and actually then doing the delay as we discussed, just so you can see how it's kind of called. Right, that's that message pump run async, and we're passing in the Lambda functions which tells how to translate and deal with the message. So, it'll be Tommy. So apparently in Norway, it's Tommy and the Tiger, not Calvin and Hobbes. So again, we sent the message. We will try and see if the event hubs are going to be any more compliant in showing us what's going on. I had a message in there already. Because I was testing it just before we started. So let's see whether or not, yeah. So there is basically, you can see we want a tiger. And if we look at the event properties of this event, you can see that the name is Tommy. So that is Tommy wanting to be converted towards it being a tiger. And again, that's just sitting there in that stream, and it will sit there effectively forever. It won't actually, there's a TTL which eventually will collect it, but we will just mark an offset. So one of the things I'm not showing you is with today, because of time, is with Azure Event Hub, you have to set up basically a storage container with a blob inside it, and you use that, well, the underlying framework will use that to store the offsets that you've read. So those came to Kafka talk yesterday. In Kafka, your client is managing that, and it's less durable, but it gets written to a topic on Kafka. Event Hubs has a different strategy of using a kind of blob storage to record the offsets for your application. Okay, so then I can run this to basically read that stream, and essentially I will get Tommy and the Tiger with any luck. Right. So Tommy effectively is now a tiger. But the key, don't worry about it crashing, but it's just the way that I exit it. All right. The key thing to understand then from those demos is the message pump, right? The idea effectively is spinning and doing translation and handling and being able to do ACK and NAC to say I've eaten the queue, I've not eaten the queue. Streams, it's a complicated topic, but you manage offsets, so you're recording how far I've read in the queue, so if I crash, someone else can pick it up. And producers sending a message, typically using an Outbox, in order to ensure that we are consistent. Okay. Pipes and filters. So one of the things about messaging applications is that I can put an arbitrary number of things between the sender and receiver, and we think of that as a pipeline. Stream processing or pipes and filters are similar-ish terms. Stream processing is mainly concerned with when you're using a stream, but pipes apply to everything. So here, what I'm doing is I'm saying, well, I'm going to send you a raise order message. Raise order message is a bit old. That's what we used to use. I'm still using the old message here. We're supposed to be upgrading to place order, but I haven't done that yet, right? So a translator just says, take the message I've got, translate it to a different format. It's very common when you're working in more complex environments that you can't upgrade everyone at the same time. So typically, actually, you're translating down more often than up to say, hey, keep everybody who has the old message informed. And enriching is another typical step. So we say the sender on the message doesn't have all the information, the receiver will need to process it. So what we're going to do is look that up in the pipe, look up some content in a data store that somebody else owns, effectively add the missing information and pass it on. Right? So here, for example, it could be that where we paid for the order, we had just SKUs and prices. We've raised that because it's been paid for. But in order to fulfill that, we're going to need to understand things like what warehouse is it in, what weight is it, what are the dimensions of the item. We don't need that right at the beginning, but the content enricher can add that in so the receiver can now deal with the actual message that you want. Okay? Yeah. Sometimes, why are they green boxes? Because sometimes that's just a little application whose job is to receive one and write the other. Other times, you find these middleware components actually are running in memory inside another application, consuming a message and then writing it out. So stream processing, you may as a term here, which is essentially when we build a stream that processes, a pipeline that processes messages in a stream. So the poster child here is something called Flink, which is really Java land. Unfortunately, there's not really a stream processor in a .NET world. And with Flink, what happens is you read a stream, typically Kafka, but it can be something else, right? And then effectively, you push messages down towards a series of what they call operations, what we call filters here. Flink calls operations, and each one of those operations you do some work. And they are transactional in the sense that nothing leaves an operator, nothing is marked as rather act on the operator until it's successfully been posted. So you get that effectively transactionally correct stream. But like I say, it's not a huge thing in .NET. It's much more you're reaching into Java tooling. Another thing you may just encounter quite commonly is splitting and aggregating. So you may find that you create a splitter which says, hey, when the work comes in, I actually want to divide it up. By country is a common one. Size of order is another one. Or if something takes a really long time, it can be difficult to observe whether or not your pipeline has basically got items that are waiting for a really long time because a component has broken. So you may break it up into smaller pieces of work. And typically, once we've split something, we want to aggregate it back. So we have something with a buffer that listens to all those messages as they come through and turns them back into something whole. So we break our order up into pieces, and it goes to separate processors, and then it comes back. We can re-aggregate the order with all the information about shipment times and that kind of thing. So, they probably don't do it exactly this way, but in the same way, when I order an Amazon basket and it's got multiple items on it, you might split those items so that they're sent to the relevant people who can tell you when they're going to ship it, etc., and then you effectively re-aggregate and pass me back the status of the order. Want to go back one? Want your photo? Sorry, mate. Managing. All right. So we're not going to go, this section here, we're not going to go into detail, but I'm just going to signpost stuff for you. So much as you have OpenAPI in the HTTP world, and OpenAPI's job is to basically document your API. In the messaging world, we have Async API. Async API's job is essentially to document it. It looks very similar to OpenAPI. If you're used to working with OpenAPI, the async API is a very similar idea. It just has some different concepts like channels and brokers and things like that. But you know all about those now, so you won't be freaked by it. But typically, that's a good idea, is to document all your endpoints. Schema registry, very important in the streaming world, should be important in the queuing world too. So a schema registry says, what is the schema of the message that I am sending? And typically, you register it ahead of time with the registry, and in your producer, when you start up, you get basically a cached version of that schema. You don't have to keep asking for one from the server in case it goes down. And you can check and say, is my outgoing message conforming to schema? If it's not, either warn or reject it. Right? Consumers can use that check on the schema. In some cases, when we're doing application-based messaging as opposed to kind of more data engineering, we may decide, I don't care as long as you can interpret it, right? Data engineering pipelines like Flink, writing to S3 tables or the like, typically are built around schema registries. There is a set of semantic conventions for messaging for OpenTelemetry, which means that as more and more frameworks begin to build these in principle, what will happen is we will begin to look very consistent in our traces for how messaging works. There's a W3C standard used for tracing. It's pretty good. There are a few problems with it. Brighter v10 ships with support for these semantic conventions. So we are now conformant. Previously, we made up our own conventions. Middleware. So middleware is the term we tend to use when we mean some kind of messaging platform or broker. On the top row, that's either a queue, like SQS, or Rabbit, or effectively it's a queue plus or it's a broker, like SNS, or it's a combination of the two. So Azure Service Bus is kind of a queue and a broker to distribute amongst multiple queues. So is Google Cloud PubSub, ActiveMQ. ActiveMQ I see less used. Underneath the streams, so Kinesis is the Amazon proprietary one. Event hubs in Kafka. Event hubs will speak Kafka. So if you want to talk to event hubs by the Kafka API, those that came to my talk yesterday, you can do it that way instead. It supports both protocols. Mosquito is MQTT, that's IoT. If you're IoT people, you probably want to use MQTT to stream out to devices like your embedded fridges. Things like Pulsar and NATS and newer kids on the block, they tend to support both queuing and streaming, and they typically run in Kubernetes environments. Frameworks, right, on the right-hand side, there's a whole lot of open source frameworks. Actually, I'm probably just scratching the surface. There is an embarrassingly large number of messaging frameworks in .NET, right? New ones pop up all the time. These are some of the ones I know about. Brighter and Wolverine and Rebus of the Mass Transit is going commercial, so we are the big three, probably open source .NET frameworks. We have slightly different opinions. That's the basic way to look at it. Particularly more about our API, but also sometimes about how we work. For example, Brighter's message pump is what we call a single-threaded message pump, which gives us guaranteed ordering, which makes us work very well with Kafka. Right? So different opinions. You just need to pick the opinions you like. That's what I would say. It's the best way to choose between the frameworks. Dapper is a beast from Microsoft, tends to run in the Kubernetes environment. And what it does is says, you may want to have multiple languages all using the same framework, so I'll do that via an HTTP sidecar, where essentially you talk to the HTTP sidecar and it does runs the message pump and produces the message for you. I'm never sure, but there you go. Just saying, ITOF Just Eat Takeaway, that's an internal messaging framework they use to wrap AWS's SQS and SNS and make it easy to use. Probably nowadays, AWS have their own framework out, and that's probably the one to use, which is the AWS Messaging Processing Framework for .NET. And even internally, the folks working on Just Saying are a bit like, yeah, we'd probably just use that one in future. And Service Bus and Mass Transit are the commercial offerings. Mass Transit, I know, has been very popular as an open source offering. And Service Bus is the kind of granddaddy of .NET messaging frameworks, to be honest, and has a lot of extra tooling, but it is very enterprisey. All right, so there you go. Hopefully that was a useful whistle-stop tour of what messaging is. The thing that happens is people get a bit frightened of messaging because they just don't know that it's pretty much like anything else. It's just I had to understand the asynchronous nature of it and then deal with it. But it is certainly, in .NET land, it is pretty straightforward to find a rich number of frameworks that will help you and support you doing messaging. So where you have those scenarios, task queue is a really good early starting point for offloading work if you are busy. But if you are microservice people, then communication between microservices that is asynchronous builds what's called a reactive architecture, and you can go and dig into reactive architectures. There's lots of information out there on the web. Thank you very much. I can do some questions up here if you want at the end, but cool.